Any questions?
What are we starting on today?
AC circuits. Any other questions?
Could you go over one of the master set questions?
Okay, for chapter 38.
The one due today.
Okay. Old 30 there. 7, 3. Apparently I don't have 30 sitting on me, so which one?
I wrote it down, I don't have the exact things, but there was.
I mean, I can bring it up if you want.
There's mine right over there on the table if you need to.
Oh, thank you.
There's 4 different parts, and someone's going in, someone's going out. The first one's, yeah.
Okay.
I don't really know how to, I know it's with the right hand rule, but I didn't really know how to do it.
Okay.
From greatest at least.
Now let's take that one, which is similar to the last one, but not exactly. All right, so they each represent 4 long wires running parallel to each other, going through the corner of a congruent square.
Seems redundant.
Yeah. Okay. I'll blame spell check. It's a square.
But it's a congruence.
I think what I was getting towards is that every square is the same.
Yeah.
Equal amount of current, I. All right, so the dots in or out.
In with the X's.
And dots are out of the board, X and.
Okay, so we have I going in, and then I out, towards you. Magnitude of the magnetic field at the center of the respective squares. All right, so right hand rule, thumb in the direction of the current, finger scroll in the direction of the magnetic field generator. So this one will have magnetic field going around like that, same with this one, same with that one, and this one's going in, so the magnetic field's going around like that.
So you don't know which direction the field is based off, you just have to know based off where your thumb is.
Yeah, I mean, you could,
It doesn't tell you what direction the magnetic field is in, right?
it does not, it just tells you the direction of the current.
Okay.
And, I mean, you could officially use Biot-Savart's law and derive it, but I find the right hand rule easier.
Yeah.
So in the middle, so at any point, let's say I take a point out here, I know the magnetic field is gonna be perpendicular to that line right there, and so at that point, it's gonna go in that direction from that current, because I know it's going clockwise. So in the middle, this one, if I draw the square properly, this would be at a right angle to each other. So in the middle, it's going this way because of that. This one is going this way. This one is going that way. And this one is going that way. They are vectors, you would add them as such. And so those two would cancel out, and you're left with whatever the value is, double that. Because I got 2 of them going in that direction.
The way I did it is I kind of looked at the components individually, like up and down, and then left and right, and then like kind of matched them up where they meet in the middle on each side, basically. And then if they were going opposite to each other, then they cancel out. And if they're going the same direction, then it's going to be
Yeah,
in
that,
that direction.
there's nothing wrong with that valid approach. You basically set up a coordinate system like that.
Yeah.
The nice thing about a square is I can set up a coordinate system like that, and it saves me a lot of math. But definitely a legitimate approach. And if you're programming something like this, well, you're probably doing something like this. Phil, you look like you have a question there.
No.
Okay.
Cause on the left side, like you'll see the arrow, if you look at the middle of the two circles, you see both the arrows going to the right. And if you look at the bottom, you'll see both the arrows going down, so then you can like kinda assume that there's gonna be more of a pull to the right, south, basically. Like the way you had the arrows drawn there.
Okay.
Yeah.
So based off what you did, all four were going in, would it be stronger or weaker?
If all four were going in, it'd be weaker.
Weaker.
Because then one of these arrows would be pointing in that direction and everything cancels.
Same with all four going out?
Yes.
And then opposite diagonals, it also all canceled, right?
The diagonals, if
And-
those are the same, they will cancel each other out. If those are the same, they will cancel each other out. So it could be, if they're out, they're in, it would also be zero.
So what combination is usually the strongest?
That potentially is, oh, no, the strongest would be because then if that's going that way, so then there is switch. Then you have that scenario. And so the net magnetic field would be down.
So they all compound together.
Yeah. Okay.
Is that one of the choices?
Yeah.
Okay.
Thanks for that.
It's C. I think.
C.
So you said that if, they're all going the same direction, everything cancels?
Yes.
Removed. Then you said if they're, opposite diagonals, it all cancels?
Yes.
So in that case, which one would be a greater, magnitude?
If there's a tie,
If there's a tie?
just put an equal sign between them.
Okay.
They're both zero.
Some people will just circle it and say tie or something, somehow indicate, don't try to leave the impression that you're saying that one is bigger than the other. If in doubt. Other questions? Then, let us talk AC circuits. So far we've pretty much dealt with DC circuits. The current's always going in the same direction. I plotted voltage or plotted current first time in a DC circuit. Well, if it's a battery, it's gonna look something like that. If it is power generation in Europe, at this point, it's gonna look like that. So the current's always going in the same direction, but if you're talking about an AC circuit, the current will be flowing in one direction, then the other direction. The current is gonna be forced back and forth.
Next to the alternating.
Yes.
alternating current.
Clever the way they came up with the wording on that. And based upon my chart here, which I suspect I got from Wikipedia, AC, we are talking, well, North America and Northern South America. And I think most of the world is DC. So let's do a couple of simple problems. If it's oscillating back and forth, then we can describe it by a sine or cosine function. Everyone's favorite. You look like you're about to ask something.
No, I was looking at the last problem.
Oh, okay. So, generally expressed as the EMF, if we're talking from the power supply, that's gonna be equal to some magnitude, I keep changing my mind on how to notate this. I'll do it this way. So the voltage from the power supply is equal to some magnitude, which I'll label as EMF, times sine or cosine, doesn't matter which one you pick, just pick one and live with it, times omega t plus phi. It's not a traveling wave, so I don't need to have the position letter to it. Phi, phase shift. omega. Let's bring back some good memories. Omega,
Angular frequency.
and this is the amplitude. Now, if you'll notice that the V I have up front is lowercase, and this seems to be the tradition. And there's one other, we're talking about AC, you tend to do if it's varying, use lowercase. So current will be a lowercase I. So it's going to be some magnitude, that's where you use the capital I times the cosine of whatever is appropriate. We'll get into that. And the other habit that seems to be prevalent in this is the delta typically gets dropped. Bless you. And so typically this would just be written as VPS. And that is a V, lowercase v, that is not the square root.
But the other one's a uppercase V.
No, they're both the lowercase v's. Kirchhoff's rules still apply. So why don't we take a look at a simple circuit here. First off, that's the symbol for an AC circuit, as opposed to DC, or sorry, AC power supply, as opposed to DC, like this, or that, and one. Depends on the operating. All right, so I have a simple just resistor in an AC circuit. I know that whatever voltage I have going across the power supply, minus the voltage going across the resistor, has got to be 0. Now it is fluctuating, but they will fluctuate together. I know that my power supply generically is epsilon times the cosine of omega t plus phi. It's got to be equal to V sub R. I know that, well, that's got to be equal to IR. So my current equation for the resistor is going to be epsilon sub naught over big R cosine omega t plus phi, or capital I cosine omega t plus phi. Nothing, I think, is particularly earth-shattering in this, which is why I sort of zipped through that. All right, dramatic pause for questions.
The circle with the wave in it, that's an AC symbol.
Yes.
It means it's AC power supply?
Yes, AC power supply. The takeaway. That is the same as that. In other words, which is the same as the voltage for the resistor, they are in phase. So whatever the phase shift is for the voltage across the resistor is the same as for the current. This is important enough for me to write up here. For resistor, current is in phase with the voltage. This will have greater importance probably later today. Okay. All that's well and good. Let's come up with something that's potentially different. We'll throw a capacitor into it, or we'll replace the resistor with a capacitor. AC power supply, capacitor. I know that the voltage of the power supply minus the voltage of the capacitor is going to be equal to 0. Because I'm going to lose, if this is the high side, that's the high side, that's the low side, so if I gain, I'm going to lose. Same with DC. So the potential difference across the capacitor is equal to the potential difference across the power supply. I know that for capacitor, let's go back to, what is capacitance?
Storing charge.
Say
Oh,
again?
wait, were you looking for the formula?
Formula,
Uh,
the generic formula.
already forgot. Q. Something.
Q over V.
Yeah. Q over delta V if we're talking about DC, or the capacitance is Q over V if we're talking about AC circuits. So this would be, so V is, this is Q over C is equal to epsilon sub naught cosine omega t plus phi. Doing some fancy math there, we get the charge, the formula for the charge is epsilon C times the cosine of omega t plus phi. And all that's well and good. But I know what you're thinking. You're going, hey, that's great, but what's the current? We really want to know the current. Well, what's the relationship between Q and current? Q and I. That's V, I'm looking for Q and I.
dq over d something.
So dq over d, what symbol should I use for something?
T.
Thank you, D. So I'll take a derivative.
It is something.
What's the derivative of my function there?
Negative.
EC sine.
No. You forgot omega.
Oh, yeah, EC omega
That's
sine.
proof we can get this. Sine of just omega t plus one. So this right here, that's the amplitude of my current, which is just I. So one thing I'm pulling out of this is that capital I, which I have generically written over there, is equal to epsilon C omega. Now, we all know, and I think I speak for all of us, love Ohm's law. So if I can get it into V equals IR form, then that's going to make me a happy camper. So what I'm going to do is I'm going to isolate my EMF is equal to I over C omega. Or epsilon is equal to I times 1 over C omega. So it's a variation of Ohm's law. Now this 1 over C omega, of course we can't get away with not naming it something. First off, the symbol for it is an X with a lowercase c there. And this is known as the capacitive reactance.
You said the X with the C only applies to the I over C omega?
Wait, say that again?
You said the X with the C only applies to the 1 over C omega?
Yes. Yeah. So it's open enough that I'm going to write over here, X sub C is equal to 1 over omega C or C omega, depending upon how saucy you're feeling. The other takeaway, let me just throw up here that epsilon. If I plot my current and my voltage on the same graph, vertical axis would be different, but we still have the same horizontal axis. Let's see, my voltage is a cosine curve. My current is a negative sign. Again, this is my current. if you'll notice, as time progresses, at this point right here, or just think about the value there, that the current is peaking, and then sometime later, the voltage peaks. So for a capacitor, the current leads the voltage, and by 90 degrees or pi over 2, whatever your will cool, pi over 2. Again, the importance of that will come in later. Yes. Questions up to here?
So what's the difference between the lowercase I and the uppercase I?
Uppercase I is the amplitude, lowercase I is the instantaneous value.
So it doesn't stand for current anymore?
It does, it's the instantaneous current. So if I want to know what the current is after 0.02 seconds, like plug 0.02 in there and I figure out what the current is at that moment. Capital I is the maximum value.
So when we did DC circuits, I was the maximum.
I was the current at that moment.
Isn't that?
Well, there were situations in which capital I was the instantaneous, but oftentimes in a DC circuit it was constant. It's just the notation, they did not consult me when they started writing it like this.
So instantaneous current, that's what you said?
Yeah.
Oh.
The lowercase values are, with talking about AC currents, the lowercase values are instantaneous, the uppercase values are amplitudes. Magnitudes, largest values. It just sits right now. You're thinking, hey, that's great, we got resistors, capacitors. Is there any more? Of course.